Professor Phillip Duxbury is professor in the Condensed Matter Theory Group at the Department of Physics, Michigan State University, East Lansing, USA. His research interests include structure determination using distance geometry methods, nanoparticles and nanoparticle dispersion, energy applications, biological signal networks, particularly the apostosis network, combinatorial optimization methods in statistical physics, and modeling of grain boundary networks in polycrystals. He has several ongoing research projects and has authored numerous papers in referred journals.
So I'll talk about some of these areas depending on how far I go, but one thing I want to cover for sure is maximum independent set and talk about the mapping between this problem, which is an NP-complete problem, to a physics problem, and talk about the bounds that are known on maximum independent set and what Grover's algorithm, quantum algorithm, might be able to do for this problem. And I want to talk about this problem, which is a grand challenge problem in materials, where we're trying to use nanoparticles for various applications. And the thing about nanoparticles is the response of a nanoparticle is very highly dependent on its structure, and it's really hard to find out the detailed atomic structure of nanoparticles. They're like big molecules, and once you have big molecules, it's very hard to find structure. So we're developing a new inverse problem, and it's very easily stated and hard to solve and typical of hard combinatorial problems. To get to, I'll first talk about this NP-complete problem, maximum independent set, and show that it maps exactly to a lattice gas problem. And in fact, all NP-complete problems can be written as lattice gas problems. It's just a question of how complex the lattice is. And that was realized, although it wasn't stated in these terms, in the famous book by Gary and Johnson, where they talked about the NP-complete class, and they talk about mappings between various NP-complete problems. If you look closely at what they do, they represent the NP-complete problems as graphs with a binary variable at each site, and in physics terms, that is a lattice gas. The spin glass problem maps to another problem in the NP-complete class called max cut, and that mapping has been known for some time and is the basis of the best exact algorithms for the spin glass problem. So this is an NP-complete class. Then I'll talk about two classes of polynomial problems, and here I'll refer to Shor, who in 2003 lamented the fact that the progress in quantum algorithms was relatively slow. We were kind of stuck with Grover's algorithm, Shor's algorithm, and ones in his class, and quantum annealing. And he said, maybe we've tried to go too fast. What we really should do is go back and try to understand how to do quantum algorithms for a broad base of the simpler classes of algorithms, polynomial algorithms. And I'll talk about how those polynomial algorithms map to physics problems. And a characteristic feature of those problems is geometry. And these are geometric problems. Percolation is a geometric problem that occurs in random media. And I'm going to talk about network algorithms that are used to understand domain walls, surfaces in polycrystals, and I'll also talk about Josephson junction arrays. And that's related because Josephson junction arrays, and in fact any system that has a monotonic IV curve, is related to a convex optimization problem, and convex optimization problems are polynomial. So there's a mapping between a very broad class of nonlinear IV curves, including transistors, IV curves, and also varistors that are solved by convex optimization. And then I'll talk about this distance geometry problem related to nanoparticle structure. Let's start at the beginning to make sure that we're talking about the same things. Graphs and networks. So a graph, very simply stated, it's a set of nodes connected by edges. So a network is pretty much the same thing. The only thing that's different is that you put a weight, some weight which depends on node I and node J. So this weight sits on an edge. So that's graphs and networks. And if you've been reading the literature, you know that there's complex networks everywhere. And what is a complex network? Well, that depends a lot on who you talk to. Almost everybody would agree this is not complex. Almost everybody would agree this is complex. This is the the network for the internet, Barabasi's work. This one here is kind of in the middle, and most people would agree, well, that's, yeah, why don't we call that complex? I will call this complex. This is a graph, a triangular lattice, which is sheared, and it's complex because it's randomly diluted. So this is the kind of structure that we'll talk about for percolative processes of various sorts. And what about NP completeness that everybody talks about? There was a series of developments in the 60s and 70s. Cook, Karp, Gary and Johnson are the lead names in that area. And Gary and Johnson classify the NP complete class as 6 problems, base problems, to which a very large number of other problems can be mapped. There are thousands of problems that can be mapped to these base problems. So I've named a few of the base problems: K-SAT, vertex cover, traveling salesman, coloring. And in general, many of these can be called constraint programming problems. So here are the features of NP-complete problems. The best exact algorithm known for any problem in the class is exponential. This number A is a constant that depends on the problem and the instance. This is an upper bound. There are many instances that can be solved in polynomial time. So in general, you don't want to go heading straight into an exhaustive search of a NP-complete problem, because in many cases you can get an answer which is pretty close or exact in a much faster time than this. This is the upper bound. There are 2 variants. There's a decision variant and an optimization variant. So for example, K-SAT is a set of clauses, and the clauses can be combined into a formula that may be true or false. And the decision problem is to ask the question, is a formula correct or satisfiable or not? That's the decision, yes or no. In contrast, the optimization variant is you have that same formula. Let's say when you do the decision problem, the answer is no. You cannot find a set of binary variables or true and false statements that will satisfy your formula. But you can still ask the question, what is the best assignment of true or false to that formula? And finding that best assignment is the optimization variant in the case where you can't find a zero-cost decision answer. The other aspect of NP-complete problems is the exact solution to decision problems, if you have one, can be verified in polynomial time. So if you got the answer and you're a good guesser, you can check to see if you have the right answer. And the key thing that makes this one class is that thousands of problems can be transformed to each other in polynomial time. Since it's an exponential time to solve one, if you solve one, you can transform it to one of the others and get a solution to the other one, maybe not the solution you want, but it'll be a solution in polynomial time. So this makes them fall into the same class only because the transforms are polynomial. And this is the most interesting feature. There is no proof that this NP-complete class is not in the polynomial class. So although many smart people have worked on this problem and nobody has found a better algorithm than exponential, it does not mean that one does not exist. So the question whether NP-complete is in P is one of the biggest outstanding problems in mathematics. And if you know how to solve that, you should go collect the prize that's out there. It's $1 million prize for trying to solve that. Be warned, though, many people have put out suggestions that they've solved it. In fact, only this year there was a claim for a solution, and it took about 3 or 4 days before a hurried internet discourse proved it wrong. These days, the disproof comes very fast, and the price is high. Putting out something that's not right, especially in a big problem like that. So now I want to talk about an exact relation of statistical physics to the NP-complete class, and in particular this maximum independent set problem. Many of these problems, in particular this one, are extremely easy to state, and they're kind of, on the one hand, intriguing and kind of annoying at the same time, because you know very quickly what the problem is, and then you can take years and get nowhere trying to solve it. So, maximum independent set. You take a graph, and what you want to do is choose a subset of the nodes so that no 2 nodes in your set lie at the ends of the same edge. So you can only have one node in the independent set on each edge in the graph. So it's a subset of the full node set that's independent in the set, in the sense that no two nodes in the set share an edge. Easy to state. Now in physics, we can think about that problem as a lattice gas problem and say, okay, I have an edge, and I don't want to have two sites or two atoms at the ends of the same edge. Well, that's certainly the case if you have a hardcore repulsion where the radius of each of these atoms is bigger, like the sum of the radii of twice times the radius is bigger than the length of your edge. So if the diameter of one of your atoms is bigger than the length of the edge, then you cannot have those atoms sit such that two atoms share an edge. So there's an exact mapping between this physics problem, which is called a hardcore lattice gas, and the maximum independent set problem, which is in a sense trivial. Now the question that we ask about our lattice gas is different than the questions that are asked about maximum independent set. So maximum independent set is one of these NP complete problems because it's trivially related to the vertex cover. Simply, wherever you have an atom or an occupied site or a member of the independent set, it's not a member of the vertex cover. So it's a simple mapping. This is a key point. This problem's been worked on for 30 years, and there's been a whole sequence of refinements of the upper bounds and practical algorithms. The best upper bound on maximum independent set is this, 2 to the 0.276n. So if you were to use Grover's algorithm naively for this same problem, your computational time would be 2 to the 0.5n, right? It's the square root of 2 to the n. So if you do a naive Grover's algorithm, you will do worse than the best classical algorithm. So the only way that Grover's algorithm is going to make an impact in this area is if you somehow combine the strategies of the classical and quantum procedures. So that's a challenge. How do we do that? And what's required? Now this is a very complicated algorithm, I should say. The way that you achieve this bound is by using a whole set of complicated branching rules dependent on the local structure of your graph. And it would be exceedingly hard, as is often the case for these combinatorial problems, to even develop a parallel implementation because they're very interdependent. It's hard to take a piece of it and shunt it off to another system. So this is a very challenging aspect of computational algorithms. So here's a picture of the maximum independent set for a simple graph. So these red sites here don't share an edge. So in that sense, the red sites are independent. I challenge you to see if you can find a larger independent set. We're always looking for maximum independent set, and the claim is that 4 is the cardinality of the maximum independent set for this graph. So the computational challenge is, given a graph, find the set of sites like these ones that do not share an edge. Now, finding a set of sites that do not share an edge is easy, right, as long as you don't make the cardinality too big. This is the maximum cardinality, and it's interesting to define a phase diagram. So you can take these sites and form a probability. That would be 4 over the total number of sites here, which is 9. That probability would be 4 over 9 for this graph. If you are at a probability or a density which is less than this line, you're in what's called the fat phase. So if I say to you, find me an independent set with one site, that's trivial. I can choose any one site and it will be independent. If I ask you to find an independent set with 2 sites, that's also relatively easy in this graph. And you're in this phase. Once I ask you to find an independent set with 5 sites, you cannot. You're then in the unsat phase. You can then try to solve the optimization problem, which would be find a set of sites such that the number of violated edges is minimal. If you have 5 sites, you have to violate at least one edge, so the best unsat solution for 5 sites in this graph will have cost 1. But you could find lots of other worse solutions. So the statement is, in this regime here, you have an optimization problem where you want to minimize the number of violated edges, and in the SAT phase here, you just want to find a satisfying assignment, and there is a phase boundary here that separates the SAT phase from the unsat phase. So I've already stated this, that the maximum independent set maps to the hardcore lattice gas, but let's write a Hamiltonian for it. Here is the Hamiltonian. This is a lattice gas Hamiltonian, and in physics language, each site on the graph can be occupied or not. So this is a binary variable, 0 or 1. And so what this says is if both of the sites, I and j, have 1 here, it costs energy j. So that's a statement of the lattice gas repulsion. If I make this infinitely large, so that the lattice gas cost is infinite, I will never have any occupied neighbors on my graph. This imposes the condition that I want to maximize the sum of the number of occupied sites. I want to maximize the density. So this is the condition for pushing me towards the maximum independent set, and this imposes the independent set condition. So these are competing aspects, and the typical competition that occurs in NP-complete problems is encapsulated in this physics problem. To really make it the maximum independent set, we've got to take some limiting cases. We have to take j to infinity so that this independence condition is strict. We have to take temperature to 0, so it's truly a combinatorial ground state rather than some finite temperature state. And this condition here ensures that I take mu to infinity, but j has to go to infinity faster to ensure the independence criteria is imposed. The other aspect of these NP-complete problems is that they exhibit a phase transition, and qualitatively, I stated that here already, there's a phase transition between the SAT and unsat phases, and this has been studied in great detail and has caused a lot of excitement and helped understand combinatorial problems more. So, in general, a graph with relatively few edges, low constraint, it's not computationally hard to find the maximum independent set. So if you have a set of independent nodes, there's no constraints. It's easy just to say each node is independent. Once you have subgraphs that are highly connected, those subgraphs make it hard. So as the connectivity of a graph increases, the computational complexity increases. And in fact, in the maximum independent set, in this regime here, the clusters of the graph where you have difficulty finding satisfying solutions are logarithmic in size maximally. So in this regime here, because the size of the clusters are logarithmic maximally in size, and even though it's exponentially hard to solve those logarithmic size graphs, you have exponential to logarithm, which is polynomial, meaning that finding the satisfying solution in here for maximum independent set is polynomial. So in here you can find the phases in polynomial time. It's no longer a hard problem. Over here actually, if you're solving the decision problem, it's also easy to prove it's unsat. So the decision problem out here is not polynomial, but it's easier than here. In here, at the phase transition, for the decision problem, it's very hard to decide whether it's satisfiable or not. So there's a peak in the complexity at the phase transition, and there's been a lot of talk of using that for encryption, where you want to find hard instances of various problems in order to encrypt information. I don't think it's been successful yet, but people at Microsoft, for example, Jennifer Chase has been talking about that for quite a while. So in the keep doing that. In the KSAT problem, this is what this looks like. This is from a paper by Vadim Shmelyensky at NASA, but it really follows work by Mézard's group in Paris, and also I think Mézard's group. Yeah. So the KSAT problem is a problem where you have a set of logical formula, and so what you want to do is have these clauses where if this is true, or that is true, or that is true, then the clause is satisfied. And you have a series of these clauses which are combined. So you want to satisfy this clause and that clause and that clause. This is a typical constraint programming problem. Each of these clauses is a constraint. There are m clauses in a typical k-sat problem. You have m constraints, and you have n variables. In this case, each one of these variables, xi. And this phase transition occurs in a very similar manner to the maximum independent set, where you have the probability that you can find a satisfying clause goes to zero at a critical threshold that depends on the ratio of the number of clauses, the amount of constraint, to the number of variables. And in the 3-sat case, this has been found for random 3-sat pretty much exactly using methods of statistical physics, replica methods, and it's known to be around 4.3. The computational time taken to solve the problem can also be estimated by statistical physics methods, and it's this curve here. And you can see there's a peak in the computational time exactly at the phase transition. This is for the decision problem. Now, when I described graphs and networks, it looked like the only interactions that could be handled would be pair interactions, because you have an edge connecting two sites. However, there's a simple trick by which you can include things like k-sat, which has 3 variables in each clause. This clause can itself be written down as a statistical physics kind of formula, where you have an or, you have a product, where you have an and, you have a sum. So this turns into a product of 3 binary variables. You add a product of another 3 binary variables. So k-sat, in general, involves products of k variables. And if you want to represent something like this, which is, this has got product of 4 variables, 3 and 3, as a graph, you do it using what's called factor graphs. Factor graphs are a generalization of normal interaction graphs we use in physics to include these many-body interactions, and it's been used a lot in probabilistic reasoning. And what you do is you put a node for each interaction. So here's the interaction with 4 terms, and you can see it's connected to the 4 variables. So you have every term in your sum of interactions is given a node of its own, and the variables have their own nodes. And this is very different than the way we usually write graphs representing physics problems, but having this notation really helps doing more complex problems. Another class of problems I thought I'd give you the background to. Ising models, been around forever, since 1919 or so, when Ising first did the 1D Ising model given to him by Lenz for his PhD thesis. And it's a binary problem in the simplest case, where the spins are up or down, and you have an interaction, which is an exchange interaction, Jij, and I'm going to talk about the general case where there's a random field at each site and a lattice and an applied field. So here's the history of this problem from the optimization point of view. So early on, it was pointed out that the general Ising model partition function can be written as a problem of counting dimer coverings or perfect matchings on a graph. And this was the basis of some of the early work finding the exact solution to the Ising model. Temperley and Castellan and Fisher. More recently, Zakina has talked about doing this in higher dimensions on higher genus graphs. You can solve this exactly in 2 dimensions because you can reduce it to a set of determinants which are easily solvable. In higher dimensions, the number of determinants you have to use grows exponentially, and so it becomes computationally hard. So what I've talked about so far are combinatorial optimization problems. How does this map to anything that people do in computer science? Well, it's another branch of computer science. These are counting problems. And there are many counting problems that are of interest in number theory and combinatorics. And one of them that's talked about a lot is the chromatic polynomial. The chromatic polynomial maps exactly to the partition function of the Potts model, and the Potts model reduces to the Ising model. So I'm not going to talk about the counting problem today, but the finite temperature Ising model also maps to an optimization problem, but it's a counting problem. So the square lattice Ising model partition function is solvable because it can be reduced to determinants and is polynomial timed for general couplings. So even if you have random couplings between the spins in an Ising model, you can solve it in polynomial time. The ground state of the Ising spin glass, which is with random couplings, in general is NP complete. This is demonstrated by these two gentlemen rigorously, and it maps to max cut. I won't show how that works. It takes a little time to derive. There is another variant of the Ising model, which is the one where instead of having random couplings here, if you make this a constant, so all of these interactions are attractive, ferromagnetic, they all want to point up, but you make this guy random, that's called a random field Ising model. And if you look at the energy as a function of configuration, for that case, the random field Ising model, it looks really complicated, just like a spin glass, qualitatively. But computationally, you can actually solve the random field problem in polynomial time. So it's an example of where the computer science of this gives the answer to a problem that looks qualitatively as hard as the spin glass problem. There's a lot of reasons why, physically why that's the case as well, but it's an interesting fact that Ogielski showed in 1986 that the random field Ising model was solved exactly. It maps to what's called the min-cut max flow problem in computer science. And this was then applied also to the diluted antiferromagnet in a field, which is the key experimental system used to treat random field problems. There's also a bunch of other ones. I'll talk a bit later about a specific mapping, this one here, where you can map the domain walls in Ising ferromagnets to this same min-cut max flow problem, which I'll also describe. Okay, so that was a quick run-through of this NP complete problem, and I want to make a few points about it. So if we're going to apply quantum algorithms to this NP complete class, we've got to keep in mind these issues. The classical bounds currently for NP complete problems are better than using a naive Grover search. So we have to have an understanding of how we're going to use quantum algorithms in conjunction with classical algorithms, or else it's a non-starter. Second statement is the geometry matters. So there are many easy instances of NP complete problems. And to understand which instances are easy, we have to understand the classical algorithms that make them easy. So a very good understanding of the classical NP complete algorithms is absolutely essential to make an impact in this NP complete, or in the use of quantum algorithms. The other thing I didn't mention so much is that heuristics in many NP complete problems, for example, this maximum independent set problem, give solutions that are accurate to a few percent. You don't need to find an exact solution in many cases. If you're happy, for example, in that independent set problem, in finding a density which is within a few percent of exact, it's going to be a little less dense than the maximum, but in many cases that you don't care for practical applications, then you don't need to even find the exact solution. You can use these polynomial heuristics and they'll do very well. The other thing I want to emphasize is that we really need a broader base of quantum algorithms that work for the broad base of polynomial algorithms that are used much more frequently than actually the NP complete algorithms, because they're very fast and very accurate for a wide class of problems. So I'm going to talk about polynomial problems for a while and how they're related to physics, and I'm going to start with percolation problems. So percolation problems, probably many people have heard of connectivity percolation. And connectivity percolation is just like percolation of water through a bunch of grains of coffee when you make your coffee. You can imagine when you put the grains of coffee into your coffee percolator, there is a network of pores that run from the top where you put the water to the bottom where it comes out nice and tasty. That connected pathway of pores is a complicated network. And if you pack the grains too tightly, the water doesn't get through. If you pack it loosely, the water gets through. And that transition from where it does not to where it does is a percolation threshold. You can make a very simple model for that on a graph where you might take, say, a square lattice. And the square lattice you can think of as pipes. Each bond in your square lattice is a pipe. You put the water at the top. If all the pipes are open, the water will flow to the bottom. If you start taking out some of the pipes in your square network, at some point you will cease to have a connected path from top to bottom. That's the percolation threshold. It turns out that the problem I just stated, the square lattice bond percolation problem, if you take out at random 1/2 of the bonds in the lattice, it ceases to percolate. So the percolation threshold for the square lattice bond case is 1/2. And there's very interesting geometric properties at percolation. Exactly at that threshold 1/2, the network of connected pipes, if it exists, is fractal. It has an interesting fractal dimension. The behavior of the probability of a site being on that fractal is singular as a function of the concentration of edges. So there's many statistical physics things that have been studied in the problem. There's a generalization of that connectivity percolation problem to other cases, and these cases typically have higher connectivity than single connectivity. So if you have this connectivity from top to bottom, flow will occur. And if it were an electrical circuit where instead of pipes you had resistors, you would get an electrical current if you have a connected path of resistors. Then let's imagine a problem which instead of being an electrical problem is a mechanical problem. Let's take a network of a square network where instead of resistors we have springs. And we're going to ask the question, if I have this square lattice of springs and I apply a stress, is it rigid? Well, if I apply a stress this way and I have springs all vertical, there will be a restoring force. So it looks like it's got a rigidity. However, if you shear it, it's going to be floppy. And in fact, if you displace the sites infinitesimally, even vertically, it is floppy. So the square lattice from the point of view of rigidity is marginally rigid. It's actually exactly at the threshold of rigidity. If you go below that and take out a few bonds in a square lattice of springs, it becomes floppy. That's the rigidity percolation problem, and there's a very beautiful geometric behavior of percolation in rigidity networks, and we found a mapping of this problem to problems in matching in computer science that changed the way we could do this problem. We thought this was a hard computational problem when we were trying to solve it, but it turns out that it's in the class P. There's another problem called bootstrap percolation, which again doesn't like low connectivity, and what you do is you pull off sites off a network until you have at least every site with at least k neighbors. This is another problem that's also treated in probabilistic graph theory. Even in the NP complete problem maximum independent set, percolation occurs. And it's a connectivity percolation in this case, and it works because you can reduce, and this is the way in which you reduce complicated graphs in the case of maximum independent set. So in this case here we've done a calculation where we started with all of the edges, both these dotted edges and these solid edges in this network. And what we're going to do is reduce the computational complexity of finding the maximum independent set of this graph, imagining that it did have these edges and sites which are open here initially. The theorem is that you can reduce this problem because any edge that is a leaf, that is singly connected, like this guy here, you can always place this site in the independent set and remove that site, this edge, its neighboring site, and its neighboring edges. And you do that recursively, and you can reduce this graph to a much smaller graph. So this is an example of reductions that are typically done in combinatorial optimization for specific graphs. And if you did this and then took what's left and fed it into a quantum computer, that might be a more efficient procedure than taking the whole thing and putting it into a quantum computing algorithm. And in many cases, what this does for lower connectivity graphs, it can actually change the computational complexity. In this instance, it did not, because we take out these sites, we still have a connected path here. It's still an extensive giant cluster, so you'd expect this to be still computationally hard. But in some cases, if this were lower connectivity, it would break these up into small clusters, and then it would make it significantly simpler to find the independent set. So there's an interesting percolation problem here. When you do this reduction, what is the concentration of graphs at which the reduced problem is still NP? And the answer is, well, it looks just like a percolation problem. This is the probability that the remaining core after leaf reduction, this is on diluted triangular lattices, where we've diluted a fraction p of the edges. In this case, the percolation threshold was about 0.465 or so. This is the probability of a site being on the spanning cluster. So what this immediately tells you in any of these problems, this regime is easy, that regime is hard, computationally. The interesting thing is that the universality class of this percolation problem is the same, as far as we can tell, as the standard connectivity percolation threshold. Now, how broad is this regime where you can reduce something that looks initially to be hard to something easy? The answer is that if you take a random graph, which is a complete graph with a certain fraction of the edges removed, the connectivity threshold in a Erdős-Rényi or complete or random graph is c equals 1. However, in this leaf removal process, we find c is 2.7. So the regime between c equals 1 and c equals 2.7 is changed from polynomial, from NP complete to polynomial by doing this leaf reduction. Rigidity percolation problem. So this is a graph problem, and we have these nodes and edges, and they're connected by Hookean springs. The springs are freely rotatable, so there's no angular restoring constants. And the graph rigidity problem, which is actually a standard problem that's studied by a very small group of graph theorists, and they've been seeking combinatorial conditions to decide when a graph is rigid. And here's a comparison of the question for the case of connectivity percolation on the left here and rigidity percolation on the right. So these structures are connected, but they're not rigid. You can clearly pull this guy upward. If these were springs and I were to put a force on here, this thing would flex. So what do you need in order to make things rigid? Well, here's some rigid examples. Triangles are typically rigid, but there are higher order structures like this guy here that is rigid. And so the question is, what in general are the conditions for graph rigidity? This is a problem that was actually looked at by the famous James Clerk Maxwell, who was an engineer, and he wanted to know how many struts you had to put in trusses in order to support a bridge. Very similar to this triangle problem. And he came up with a very simple counting argument. He said, okay, let's say we have n nodes in the graph representing my trusses in 2 dimensions. Each node has 2 translations, 2 degrees of freedom. I'm going to treat each connection, which each bar or each beam, as a constraint. if I have enough constraints in order to constrain the degrees of freedom, then it will be rigid. So whenever 2n minus b is small enough, it should be rigid. Now what's this 3 due to? That 3 is due to the global translations and rotations of something in 2 dimensions. So my bridge can be internally rigid even if I could translate and rotate it. So it's the internal rigidity that's the key thing. Then you can pin your bridge down anywhere you want to put it. It's internally rigid. There is one thing, however, that Maxwell did not treat and was treated later in the mathematical community, and that is the fact that this counting is not right if some of these constraints are degenerate, or in graph terms, redundant. So the algorithms to find whether a structure is rigid or not do this constraint counting with the additional feature of taking into account redundant or unnecessary edges. And that's something that was developed in the math community, engineering math community. There's a famous theorem due to Larman saying that, well, in 2 dimensions, you can do a test as to whether a structure is rigid by testing all subgraphs to make sure none of them have redundant bonds. And there's been a series of developments based on that which enable us to find rigid structures in 2 and 3 dimensions. So the procedure is to match degrees of freedom to edges, and I don't think I'll go through the technical details of that. Here's pictures of what rigid structures at percolation look like compared to connectivity percolation structures at the same threshold. As you might expect, you've got to have a lot more edges in order for something to be structurally rigid compared to connected. Let me say a few words about network optimization problems. So these algorithms were developed, at least the convex optimization algorithms were developed starting in the 50s and 60s, which were a heyday of network flow algorithm development. And it turns out that physicists have rediscovered algorithms for solving essentially the same problems, and it's only been in the last, and they were rediscovered in the 60s and 70s, and it's only been in the 80s and 90s that people have realized, well, you know, they've had these algorithms for quite some time. So let me define some of these basic problems for you. So we're going to work with networks now. So imagine a network where each edge has some weight. And the weight is often called a cost in network optimization. So each edge has a cost. The minimum spanning tree is a tree that reaches every edge in the network, but has minimal cost. The shortest path between 2 points is a path along which the sum of the costs is minimal. And the maximum ST flow in a network has a slightly different definition, and instead of a cost, which is like an energy, if you think in physics terms, this is a flow capacity. So each pipe in your network has a flow capacity. And this is important for things like traffic flow, the capacity of communication networks. So you imagine you have a warehouse here, you have another warehouse here, you have a network. Each edge in your network is a road that has a certain capacity. What is the maximum amount of stuff you can move from your warehouse here to your warehouse there? Now, if you think about that problem, there is some bottleneck in your network that will limit the amount of flow that can go from here to here. And that bottleneck, it turns out, is a surface. And it's the surface on which the sum of these capacities is minimal. So that's why it's called maximum, well, I didn't write it here. It's called minimum cut, maximum flow. So the minimum cut specifies the maximum flow. Min cut, max flow. So it's one of these mini-max problems. And in physics, there are problems that are one-to-one in correspondence with these 3 network optimization problems. So here's an example of a physics problem. This is, again, a randomly diluted network. And I found this is one path on a minimum spanning tree in this network. It turns out that the paths on a minimum spanning tree in this network are the same as the paths on percolation networks, connectivity percolation. So these paths are the same as the paths in percolation. And we wrote that and proved it rigorously there. Moreover, if you grow these networks using standard algorithms from network optimization, it turns out these networks are the same as growth algorithms in physics. And the growth rules are slightly different for minimum spanning tree, which is on the left here, and shortest path, which is on the right here. You can see that what this growth algorithm produces is a highly fractal structure. This growth here turns out to be exactly the same as Kardar-Parisi-Zhang growth, which is a growth algorithm for materials growth and also bacterial growth, Eden growth. And the paths that occur, that are generated here, are these shortest paths. These shortest paths also apply in physics to things like pinning of flux lines in disordered media. So this is starting to fly along pretty fast. It turns out that these paths, minimum cut and maximum flow, map to rather interesting structures that occur in nonlinear networks. So here's a nonlinear network. This is an IV characteristic of a Josephson junction. I've lost the I here. I don't know where it went. Okay, there's an I down here. So in Josephson junction networks, once you get to a critical current, a voltage occurs. So this is the characteristic for one junction. Now let's imagine we have 1 million junctions, and we want to find the critical current across the whole network. And it occurs somewhere down here because there's some limiting path through the surface that limits the total current that can flow through my Josephson junction array. Now it turns out that critical current occurs on a surface, and that surface turns out to be exactly the same as the minimum cut that I just talked about. So the threshold current in these Josephson junction arrays is exactly the same as this classic min-cut max flow problem. You can do a bit more. You can look at higher order voltage effects. So if you crank up the voltage beyond this, you get other surfaces. These are filamentary surfaces. Voltage is localized on these surfaces in these arrays. By the same token, filamentary flow is very interesting in things like RRAM, dielectric breakdown, and other things. And it turns out, varistors are another example, where now you have a threshold voltage at which you suddenly get a current. So you put enough voltage across a thin film, eventually you get a current. That's filamentary flow. In a disordered system, if you have these nonlinear characteristics, it turns out that the flow is localized on these filamentary paths, and the first path that lines up here is the path along which the voltage threshold is minimal. So you sum up the voltage thresholds along this path, and the path along which that is smallest is the onset of your filamentary flow. That is exactly the shortest path problem that occurs in network optimization problem. So this is a classic problem, and here we're trying to find atomic structure. The atomic structure of proteins obviously is extremely important, and the gold standard for finding atomic structure is crystallography. In many cases you can't crystallize proteins, so you try to do it in solution or with non-crystalline samples. And in those cases you use NMR. And NMR gives you interatomic distances. It's been very successful in the case of proteins. However, if you try to translate that same technology to finding the structure of something like this, and this is an example of a manganese atom embedded in cadmium selenide, which is of interest for various quantum dot and other applications, then the difference is, over here we have the protein sequence. So we know, we can figure out the endpoints of each distance. In this case here, if we get a distance list from experimental data, typically we don't know the endpoints of each distance. So this combinatorial optimization problem is much harder than this one. Now, they would love to also be able to solve this problem without knowing which endpoints each distance corresponds to, because the process of assignment, which is what you need to do here to figure out the endpoints is tedious. What we're working on is this unassigned distance geometry problem. And in general, we're working on the nanostructure problem, which is the general problem of inverting experimental information to find atomic structure in non-crystalline material. Where do you get these interatomic distances from? Well, there are a variety of techniques, but one that we've been using as a test case is called the pair distribution function analysis, which is extracted from powder diffraction data. So this is powder diffraction data. You invert it, you get a pair distribution function, and it turns out that the peaks in this pair distribution function are location of interatomic distances. So this peak here, which looks like about, there's 5, so it's about 1.1 or so angstroms, is actually the nearest neighbor distance of carbon. This is the pair distribution function from a fullerene. Now, if we take this data, we can further analyze it and get a set of peaks out of here. So this is now a list of interatomic distances. Here they are. So the problem we're trying to solve is this one. Given a set of distances, can we find the structure? And there are two limiting cases. The case where we have high symmetry and a case where we have no symmetry. This is a random graph where all of these distances are unique. And we've gone through a whole bunch of different techniques to do this. We developed our own algorithm, which is a dynamic programming procedure. Standard algorithms did not work, and I want to emphasize problem structure is absolutely critical. You get nowhere in many problems like this, and in this one in particular, without really getting into the details of the problem. So we have a combination of tournaments and dynamic programming with annealing, and in that way we've been able to invert structures up to about 100 atoms. And here's the example of how you reconstruct a fullerene. It's a procedure where you build up the structure and then backtrack to remove atoms that are poorly placed. And this is the final structure we got with that experimental data. And these are various other things we've solved. And our goal is to extend this to a general problem solution where we include as much data as we can. The data we're including at the moment is this data, pair distribution function. There's a wide variety of other data. This all needs to be fed into a global optimizer to get the best estimate model. This needs to be verified and fed back. This kind of problem, this is a grand challenge problem to see atoms in non-crystalline materials, and it's been dubbed this nanostructure problem. And that's the sort of problem we'd love to solve with quantum computing. So let me close by making a few remarks. I hope I've shown you that there's really a great deal of overlap between statistical physics and algorithms in computer science, very rich both in terms of algorithms and in terms of concepts. Combinatorial optimization and counting problems occur in both fields. Now, the dialogue is actually time-consuming. It's really hard to understand what people in another field are saying, and I've had many instances, and probably other people have had many instances of spinning wheels when talking to people outside the field. It's a gamble, but in many cases, it's a payoff. There are a couple of centers that do a very good job of this. The Schloss Dagstuhl in Germany, I've been to a couple of times. They run very good schools. And Dymax at Rutgers, so if you're interested, you can find schools there. And in the context of quantum computing, I want to say again that in NP-complete problems, the classical bounds are currently better than doing a naive Grover search. So we have to work together. We have to combine Grover and classical strategies in order to make progress. There's also many cases where NP-complete problems are easy, and it's really important to understand why they're easy, and what algorithms are necessary to make them easy before we start using quantum algorithms. There's also many cases where heuristics give a very good solution to within a few percent. You don't need, in those cases, or in many cases, to actually get an exact solution for practical problems. And this remark, which Shaw made in 2003, progress in quantum algorithms may be better served by going back and trying to find quantum algorithms for many of these P problems, enabling us to build towards more complex problems. Thank you.
We have time for one question.
Has that been applied to the case of a breakdown with a laser? where you actually have a strong field that's somewhere in the middle, not at the ends, and you also get these filamentations. Clearly, if you hit it hard enough, you blow the living daylights out of everything. But can you say anything about the onset, and so that you can be reproducible?
Well, okay. Anything to do with breakdown is inherently not reproducible. And so, for example, even in the shortest path, let's say I was to change one of the edges, the weights, the costs on one of those edges, the filamentary path you get is very different. So it's chaotic in that sense. But the statistics are the same, like the roughness of the path, the number of edges in the path. So it's only a statistical description that is the same. It hasn't been applied to the laser case.